Hello, my name is Eunjune Lee, and I am an independent researcher affiliated with Seoul National University of Science and Technology in the Republic of Korea. Before I start my presentation, I would like to express my sincere gratitude to NTUA for organizing this conference. The title of my presentation is Conceptual Design for a Hybrid Wave Disk Engine and a Variable Chunk-Based CFD Methodology. In today's presentation, I will discuss the hybrid feedback mechanism and hydrogen application for the wave disk engine. Furthermore, I would like to propose a new CFD mechanism that is expected to be a powerful analysis tool for fluid dynamics and shock waves in the wave disk engine. Please note that while the theoretical methodology of this mechanism is defined in this study, the implementation of a specific CFD code, mathematical analysis, and detailed evaluation are beyond the scope of current research. Now, let me begin by reviewing the previous wave disk engine concepts and mechanism. The initial concept of the wave disk engine was proposed by Michigan State University. The wave disk engine is an internal combustion engine that compresses and expands the gas using shock waves and centrifugal force generated within the rotor channel rather than a piston compression process or a turbo machine. It aims to provide a microscale, highly efficient mechanical power generation and electrical output. The wave disk engine is composed of a thin, flat rotor with curved channels, enclosed within a disc-shaped engine shell. The gas moves through the radial rotor channel. The wave disk engine uses the shock wave generated by the channel's fluid dynamics and the internal combustion process. It improves efficiency and simplifies the structure and processes by eliminating the piston or turbo machinery and reducing the number of energy conversion steps compared to conventional internal combustion engine or gas turbines. In addition, this structure can effectively leverage centrifugal force by enhancing fluid flow and supporting the self-driven mechanism. The figures shown on the screen are a diagram of the wave disk engine and its fluid dynamics. The rotor, composed of curved channels, is shown in the figure on the left. The combustion air intake is conducted through the disk hole in the middle of the disk rotor. The fuel is sprayed inside the channel where the intake gas exists. As the spark ignites the channel, the fuel burns, increasing the gas temperature and pressure. After combustion, the high temperature and high pressure gas is exhausted through the ports on the circumference of the engine. The combustion of the gas causes a rapid local pressure spike. Under conditions where the pressure gradient between the surrounding air sections is extremely high, a shock wave is generated. The shock wave is reflected off the closed rotor walls, further increasing the gas pressure and temperature. As shown in the figure on the right, when the exhaust port is opened, highly compressed gas is expelled through it, producing jet propulsion. My research can be divided into the hybrid wave disk engine system and the variable chunk-based computational fluid dynamics mechanism for the wave disk engine design and analysis. To begin with, let's look at the purpose and concept of the hybrid wave disk engine. The purpose of constructing the hybrid wave disk engine system is to propose an electrical feedback system for the wave disk engine and hydrogen fuel. Hydrogen is a substance that has rapid combustion propagation. Furthermore, hydrogen's gravimetric energy density is significantly higher than that of conventional fuels such as gasoline or diesel. In this research, I considered a method that uses hydrogen as a substitute for conventional fuel. The feedback and control system focuses on stabilizing the engine RPM. In a wave disk engine, the rotational speed of the rotor is one of the conditions that determines the residence time of the gas and shock wave. The electrical system monitors the angular velocity and changes the system mode. When the RPM exceeds the target angular velocity, the system acts as a generator, converting mechanical energy into electricity. Conversely, when the RPM falls below this target angular velocity, the system serves as a motor and accelerates the rotor. While a conventional engine uses a Brayton cycle, the wave disk engine uses an Atkinson-Humphrey cycle. The fundamental advantage of the Atkinson-Humphrey cycle over the Brayton cycle is that the heat addition leads to an increase in pressure due to volumetric confinement. Because of the pressure gain from combustion, the Atkinson-Humphrey cycle has a much greater expansion ratio than the compression ratio. This allows Humphrey cycle engines to produce more power than a Brayton cycle engine with the same inlet states and the combustor. This is why we can expect the Atkinson-Humphrey cycle to have higher efficiency than the Brayton cycle. Now let's look at the structure of the hybrid wave disk engine system shown on the screen. Here, the black lines represent the hardware components, while the red and blue lines represent the software and electrical power connections. The angular velocity of the rotor is measured by the photo gates in real time. The measured velocity data is passed to the velocity feedback controller, which regulates the mode of the velocity controller motor. Up to this point, I have discussed the electrical feedback system for engine RPM regulation and the implementation of hydrogen combustion. However, to reflect the shock wave generated by the extreme pressure increase and rapid propagation of combustion, a conventional Euler method using mesh analysis can easily lead to numerical divergence and calculation failures. Furthermore, for the wave disk engine, where the shock wave is one of the most important factors, a grid-based method is not appropriated, as it blurs the shock boundaries. Therefore, this research proposes the variable chunk-based computational fluid dynamics methodology, which is a new numerical analysis framework. The variable chunk-based CFD method is fundamentally a particle-based approach. It divides the fluid into finite, specially shaped chunks and analyzes the dynamics of computational particles representing each chunk using the Euler-Lagrange equation. It computes the effect of the shock wave by applying shock relations or the method of characteristics. Now, let's compare this novel CFD method with the conventional approaches, the Navier-Stokes solver and smooth particle hydrodynamics. The Navier-Stokes solver is an Eulerian-based solver that analyzes the fluid using a stationary grid. Therefore, it can achieve high accuracy and resolution in the boundary layers. However, due to the limitations of grid method, several problems occur, such as diffusion of the shock wave surface, high possibility of grid divergence, and complicated process of setting the grid and initial conditions. SPH is a representative particle-based method. It uses the Lagrangian method that analyzes the fluid from the perspective of the moving particles. It can achieve a sharp surface of the shock wave, short pre-processing times, and a low possibility of grid divergence. However, it suffers from low calculation cost efficiency, accuracy, applicability for various situations, and stability in supersonic conditions. Variable chunk fluid dynamics solver utilizes the Lagrangian method, focusing on the moving variable chunks. Theoretically, this novel method is expected to reduce the computational cost of SPH because the number of particles that the solver should compute decreases. Since this method is a kind of particle-based CFD, it also retains the advantages of capturing a sharp surface of the shock wave, low divergence possibility, and prevention of fluid dilution. Conversely, the weaknesses of this method are the cost of calculating and determining the initial shape of the chunk, divergence risks in supersonic conditions, and limited application situations. Now let's move on to the example. I used a one-dimensional source shock tube problem to theoretically apply the variable chunk-based CFD method. The problem is a representative one-dimensional CFD problem for testing the accuracy of computational fluid codes. The fluid located in the left channel has high pressure and density, while the fluid in the right channel has low values. Initially, both fluids are stationary. It aims to observe discontinuous fluid dynamics after the diaphragm is removed. Observing the source shock tube problem, the fluids in the two different conditions should not be mixed. In the variable chunk-based CFD method, this can be achieved by setting each chunk to the shape of the tube. Let's assume that the cross-sectional area of the chunk is identical to that of the tube and it has a micro-thickness. Then the computational particle, which represents each chunk, will be placed in a row. Two adjacent particles along a single dimension cannot bypass each other since the electromagnetic force, which represents the interaction between these particles, is inversely proportional to the square of the distance. Therefore, the fluid will not be mixed theoretically. In the shock wave generated in the wave disk engine channel, the shape of the chunk can be designed as a spherical shell with micro-thickness or using the cross-sectional area of the channel. If the chunk shape is chosen as a spherical shell, the position of the computational particle is fixed at the exact points where the combustion occurred, meaning individual particle motion alone cannot account for wave reflection. Therefore, to analyze it, the wave analysis should be applied to the chunk dynamics, making it easier to capture the effect of the reflection. If the chunk shape is represented with the cross-sectional area of the channel, it can be analyzed in the same way used in the source shock tube problem. To conclude, I would like to summarize the key propositions and findings of this study. First, applying a feedback system using an electromagnetic mechanism is expected to successfully stabilize the rotational speed and efficiency. Second, due to hydrogen's high energy density and rapid flame propagation, hydrogen is theoretically confirmed to be a suitable fuel for the wave disk engine. Third, the novel proposed variable chunk-based CFD framework offers a more effective approach for analyzing shock waves in a hybrid wave disk engine. Finally, my future work will focus on the evaluation of the variable chunk CFD method alongside both numerical and experimental analysis of a hybrid feedback system for a wave disk engine. Lastly, these are the key references regarding the source shock tube analysis, wave disk engine structure, and thermodynamics. Thank you very much for your time and attention. If you have any questions or would like to discuss my research further, please feel free to contact me via email using the address provided on this slide. Thank you once again.